Let us talk about moving the camera to a desired position. This is called computer viewing. There are three aspects of the viewing process, all of which are implemented in the pipeline. The first one is to position the camera. Setting the model view matrix. The model view matrix defines where the position of the camera is and where the camera is looking at. The second step is to select an appropriate lens. This sets up the projection matrix. The third step is clipping. Clipping decides what is visible to the camera and what is not. Unlike the real world, where a camera looks as far as possible, in computer graphics we have a finite clipping volume. It is clipped at the near end, at the far end, and also on the sides and on the top. In OpenGL, initially the object and camera frames are the same. The default model view matrix is an identity matrix. The camera is located at the origin and points in the negative Z direction. We have talked about this multiple times in the previous lectures. OpenGL also specifies a default view volume that is a cube with sides of length 2 centered at the origin. So the cube goes from -1 to +1 in the x direction, from -1 to +1 in the y dimension, and from -1 to +1 in the z dimension. Hence the default matrix for projection is identity. The default projection is also orthogonal, which means that objects that are near will appear of the same size as objects that are far. This is also unlike the real world, where objects that are far appear to be smaller than objects that are closer to us. And in the default projection, the projection plane is placed at z is equal to 0. So from ±1 in the xy dimension, this is our projection plane, and everything that is within our viewing volume will be projected onto this plane. Everything that is outside the ±1 cube, such as this object, would be clipped out and will not be visible to us. So what if we want to look at something that is outside the default viewing volume? For this, we will need to move the camera or define a different type of viewing volume. If we want to visualize objects that have both positive and negative z values, we can either move the camera to the positive z direction, translate the camera frame to achieve this, or we can move the objects in the negative z direction. That is, we can move the objects further away so that they are visible to the camera. This is equivalent to translating the world frame. So both of these views are equivalent and are determined by the model view matrix. So if we move the entire world with respect to the camera is the same as if we move the camera. These are both defined by the model view matrix. If we want a translation, we can use this translate function and pass on the translation along the x-axis, the y-axis, and the z-axis. And this will generate for us a model view matrix that will perform the translation. If you want d to be greater than 0, we move the objects in the negative z direction. This slide shows the moving of the camera graphically. So default frames, by frames we mean the coordinate frames. So the default frames are like this. We have the x, y, z axis and the camera placed at the origin and pointing in the negative z direction. Once we perform a translation of the camera by -t, where -t is greater than 0, it moves in the positive z direction, and hence now it is looking at the origin. And if we had our cube, the viewing volume here, our camera would be well outside the viewing volume and will look at all the objects that are present in the viewing volume. Now we can move the camera to any desired position by a sequence of rotations and translations. For example, let's say we want to move the camera to the plus x-axis looking at the origin. Hence we'll perform a rotation first. So the camera is initially here. We will rotate the camera, so now that it is looking from the plus x-axis towards the origin, it will still be here. The rotation, after rotation, the camera would still be here, and after that we'll perform a translation by D. So our model view matrix would look like this. First a rotation matrix and then a translation matrix. So we rotate the camera first, so it looks like in this direction, still at the origin, and then we translate it over here. So this is the OpenGL code for moving the camera, as we explained before, in the positive x direction, so that it's still looking at the origin. To do this, we use the mat.h provided with header file provided with the book. We use the translate function to make a matrix that will perform a translation in the with minus d in the z direction. It will give us a matrix T, which is of course of type mat4. And then we say rotate y, which is a rotation about the y-axis by 90 degrees. So rotation about the y-axis will make the camera still pointing up in the same direction, and will make it look into the negative x direction. And finally we combine these two rotations, the t and ry. So first is the rotation, we apply the rotation first, and then we apply the translation, and by combining these two 4x4 matrices we get a final 4x4 matrix, which is our model view matrix.